that closest point.
Sorry,
I put out a new.
forget that.
Yeah. I put out a new discretized patch release that has a new. It's using a KD tree by default to look up for closest points. It's better for. It'll be better for repeated searches on meshes, like using that closest point index. And also, there was a small bug originally with the first implementation that we pulled in that didn't work for 1D. And then I fixed that as well. But that new patch release is all out. And then we were able to pull in the cross gradient pull request from over a year ago. So it's all in, it's pulled in the SimPEG now, tested, it works, covered. We got some stuff going with it, it works well. And I also really quickly snuck in a joint total variation regularization function in there as well. So more options for joint conversion.
Yeah, I was going to ask, what's the core of it? What GTV that does?
Joint total variation. It's think of it as like joint sparsity. Like it encourages the models to be non-zero in the same location. Or it encourages their gradients to be non-zero in the same location.
It's like a dot of the two values, or?
No, they're pushed together by the square root. So, sorry, I've got to get over really quick. So it's the magnitude of each of the gradients of the two models added together plus a regularization, like an epsilon value, and then it's all square rooted. So they're coupled to the square root. So it's like, it's very similar to an L1 norm on the gradient. It's just that they're encouraged to occur in the same way like that.
Cool, man. That's awesome.
And running some of my first inversions with it seems to work pretty well as well. Like it's going to require some updates for the directives a little bit more, because we'll have to approach it the same way that we approached the like how you approach the L1 sparse solutions before them. So we'll have to get those gradients updated. Or just that we'll have to get more directives on that, or at least apply them to that, make it a little bit more general. That's what I've done with SimPEG the last week.
Nice, that's awesome, Joe. That's huge.
Yeah, it'll be good.
So version 0.16 with more joint before the end of the year.
Oh yeah, I was just running a few quick tests myself, playing with it a little bit more, and then I'm going to tag the release just when I get home.
Nice.
So 0.16. I've updated. Oh, I also updated all the tests that were done to stop, like to not test as deprecated things that are actually going to turn into errors now. So your codes will likely, if they're using any of the deprecated functions before, it's going to break.
Fair enough. Nice.
Okay, that's all I got.
Yeah. John, I see you next on my screen.
No, I don't got much to report. Just still playing with the parallelization on my end here with our own our own custom workers. But other than that, nothing too SimPEG related yet.
Good. Devon?
No, I don't really have anything much for SimPEG. I was working on a lot of, I guess, time domain stuff for with Anglo Ashanti, but nothing really transferred over to SimPEG, so I don't have much for this week.
Dom, anything on your hand?
More MT. I finally deployed on Azure to start checking out the parallelization there. It seems to sort of work. There's a lot of dead spots though on the MT implementation, so I'll need to diagnose, profile the code a little bit more. But yeah, that's it.
Good. Hey Sergey, good. How have you been? What's on your plate?
I was actually revisiting that EM1D code, and now I'm actually motivated to rework because I need to use this. So yeah, I'm making actually quite a bit of progress. So yeah, Joe did a lot of work, but what he worked is not really transferred to the stitched problem. So I'm kind of working on transferring his optimization into the stitched problem. So which is sort of the major use on my end. I don't really use much the individual 1D problem, but basically like many 1D soundings to invert. Yeah, I think I'm getting pretty close to finish up. So I made a pull request, and I think most of the tests are passing, except some of the tests are not related to me, which I'm not sure, I guess. Where are you on, Joe? Are you kind of have you fixed most of the tests, or is that something that we need to take a look?
Everything's passing on master right now. If you want to pull it in.
Right.
There's a few things that were not, so just pull master and it should be good. Like the tests that were outside of that were not passing.
Okay, sounds good. Then I'll pull the masters, and yeah, either Joe or Dev, if you have a chance to take a look and kind of, I don't know if that looks good, then we can merge into main. That will be nice.
So Joe and Sergey, just by curiosity, what was the optimization change that you made for the 1D EM?
As far as I understand, what Joe did, kind of he sort of stored some part, like a coefficients of the 1D. If you think about that, like this propagation matrix and stuff, there are quite a few things that you can basically store. I was computing most of things on the fly. So Joe has stored that and then reuse it. And then some of the optimization was done because there's if they have if the source, and I think if the receiver height and source height is not changing, even though you got many receivers, if the height is fixed, that the coefficient doesn't really change. So you can actually, in a way, you can actually optimize that process. Also, if you got low moment and high moment, for instance, although they are two different data, but all you need to compute is just a step response. So you can actually share quite a bit of part. So I think what Joe did, basically kind of figuring out all of those shared part and then just computing once. Yeah, that actually makes quite a bit of progress in the code. But that means that kind of that idea needs to be transferred to the stitched code, which actually calls each individual 1D problem. So what I was working on, basically sending the stored coefficients to the main whenever I to just store on the whatever parent node. And whenever I compute on the child, just transfer that. So I just do kind of back and forth that communication. That's what I was working on.
Nice, thanks for
the other big optimization was on the gradient side. Like the Jacobian calculation is much faster than it was before.
And also Joe has written the gradient, the sensitivity for mu and the height of each cell, each layer, and right. So that actually I haven't implemented yet, but all the mechanics are sort of ready. So basically kind of implementing that into a stitched code. So I think this is potentially might be an interest of you because you may want to invert for both mu and conductivity. And that actually implementation now is relatively straightforward. Was it? And the other cool thing that Joe did was the idea of time domain code. we first compute the step response, then convolute. And the way that I was convoluting was kind of basically integrating that numerically. That's what I was doing. And I was doing that on the fly. What Joe did actually that kind of make that as a kind of linear operation. So you can actually form a matrix. And then once you got the step response, you can just multiply that. And what's kind of cool, the same idea can be applied for the 3D code. So, because all this idea of setting up the waveform and then, what is the time discretization? That's kind of cumbersome. And also it's really dependent upon like whether you're an expertise of this. Even if you're an expertise, that's a pretty challenging process to set the right time interval. But I think it kind of makes the problem much easier. So what you need to do, you just make sure have a time step that can handle the step response, which is somewhat easier, I think, compared to with the waveform. So that's what he did. And but what's actually nice, once you form that, if you got all of sources sharing the same waveform, you just need to form once. And then you can just multiply that for all of the step responses. So that can be quite fast. And also in 3D, you can actually remove a lot of time channels, time steps that are needed to calculate the complicated waveforms. So yeah, it's kind of, that's where am I. And kind of speaking of that, the other thing that I needed for now, for the like the project that I'm working on is the tiled 3D AEM code. I wrote it before, but it's kind of like outdated. So I'm going to rework on that. And the idea is similar. Like, as I said, I'm just going to evaluate the step response for the local problem. And then once I got the step response for all of the sources, then I'm just going to multiply this projection matrix once in the parent node. So in such a way, we can kind of like quickly run the 3D AEM simulation. So that's sort of what I'm kind of working on now. And yeah, because at this point, I need a quick, fast 3D simulation code. Not the inversion code yet, but at the point when I need, I probably revisit that. Anyway, that's where I'm at.
Brilliant. So does it mean that the time discretization, it only needs to be as fine as your shortest recording? Is that the idea? So how is the time step decided?
I think what I have found the best is actually changing the time step each time, because like if you kind of logarithmically increasing the time step and slowly, you'll need like a multiple time steps. That's sort of the best. But I think for most of the AEM case, we can even fix the time step that's well designed for the AEM, for instance, and then just use it for most of the AEM case. That's what I was doing, and that kind of works in most cases. But that most cases, I'm not sure it's enough sampling. But that's still a question I don't have a good answer, because it obviously depends upon the conductivity structures. But I think if you kind of put enough sort of time steps, then so I think my idea is like you make this problem very small. Then number of time step doesn't really matter too much. Like we can just have many time step as needed. So you just put enough time step that can be used for many different cases. Then that could kind of sort of ease this discretization issue. That was just something like sort of the idea that I have now.
Cool. Yeah.
But there could be a smarter way to automatically design the time steps. That's probably better, but that I am not sure how to do.
Yeah, sounds good.
Nice. So last year, so for me, no much update on the code. I just spoke for way too long this morning. That's for the amino. So that's but I think that went well. I think people liked it, but I was way too long.
I have to go watch it.
Nice. Yeah, it was early in the morning for us.
Oh, me too. Sorry, Thibaut. I'll watch later.
No worry. Anyway, as I was telling John, in my mind, I was talking to YouTube. It's like I know a lot of people. Most people are gonna watch it through YouTube. So it's all fine. Anyway, like I was trying to get a time that was both okay for North America and Europe as well.
Yeah, I think a lot of European crews may watch, I guess, in real time. That seems like what I've heard from Alan, because they are, to maximize the participants, they're aiming to sort of European time, not the Pacific time.
Yeah, I just didn't watch at all how many people were actually connected. I have no idea how many there were, to be honest. Just got a few questions at the end, but it was getting long. So that's it for me.
That's good.
Are you guys coming to AGU? Any of you are coming to AGU?
Nobody in person.
Virtually.
Nope.
No, but the online. I'm not going either.
Wasn't planning, no.
So only Joe, I guess, and Lindsay.
Yeah.
Let's see. Gotcha. Yeah, it's a bit of a mess, the organization this year. It's kind of charting on a session. This is my first time, and yeah, it's just like it's just a mess. Like, and then the fact that they're doing that hybrid, that makes even more complicated. But we are, I'm organizing one kind of a discussion session, and I figured out that that could be open to anybody. I'm not sure that's kind of what they want, but the system they made, I think it could be open to anybody. So I'll share a link. I think it's on Monday, the next Monday. So if you guys can come, it'll be it's an open source session, and Leo, the sort of like the major developer of Veriando, is going to talk about his sort of practices. And also the other guy who's going to talk is from what's called Pythia project. It's an educational project focusing on like a more climate science, but on the education side. So he's going to talk about like how kind of he's learning from the PenGeo project and how to deal with the big data and how to transfer the knowledge into kind of educational resources. And there are quite a few other interesting posters, like from USGS. They are developing airborne EM database, how to transfer the data that they have into some sort of database, so that kind of exporting that data into or sharing the data into the other people or other scientists can be easier. I think they're focusing on airborne data. So it kind of covers airborne gravity, EM and stuff. So yeah, it seems like an interesting session. I'll share the link, and if you guys are interested, have a look and can come.
Sounds good.
And Joe is giving a poster as well. In that session.
Oh, yeah.
It seems like your poster is empty. It took a look.
Oh, I need to put stuff on. I
like,
hit publish, and I'm like, I need to finish it.
It's like Joe's poster only have like the big titles. I thought, this is probably the new style.
Yeah.
Make you think.
Slap a QR code in the middle.
Just go somewhere else. No.
Anyway.
Great. Is it our last meeting before Christmas, or are we gonna have another one? You guys are probably next week, yeah.
I mean, next week, what's the 16th, 15th?
Yeah, that's gonna be the last one. Sounds good.
Sounds good.
All right. Catch up later, guys.
Thanks, everyone. See you tomorrow.
Bye.